last week we learned about a concept called impulse. What do we define impulse as? Real quick, just give me an answer. Yep. Yeah, it's the change in momentum. How much momentum is gained or lost by something. Yesterday, you learned about a new concept called conservation of momentum. The law of conservation of momentum said that momentum can't be created or destroyed. In other words, the total amount of momentum will remain the same. How do we reconcile these two concepts? The one that we did last week, which talks about the change in momentum, the gain or loss of momentum, with the concept that we did yesterday, which says momentum doesn't change. We got changing momentum, and then we have momentum always stays the same. What's the difference between these two concepts fundamentally? Last week, go ahead, Josh. No, it's a good guess, but last week we talked about impulse in quite a bit of detail, and we looked at when we have one object, or even when we have two objects. When we have a couple of objects in a problem involving impulse, we learned that we have to pick an object, right? That means that object will gain or lose momentum, and the other object involved in the collision or whatever's going on will gain or lose momentum as well. In fact, it'll gain or lose momentum the exact same amount as the other one lost or gained. Bottom line is, when we're looking at impulse, we're looking at an object, a single object. When we're looking at conservation of momentum, we're looking at all of the objects together, the system. So if object A collides with object B, and A gains 10 units of momentum and B loses 10 units of momentum, then the total amount of momentum remained the same. Impulse we use when we have individual, or when we're analyzing individual objects. Conservation of momentum we use when we're analyzing a system. Specifically, and Josh alluded to this word earlier, what kind of a system? An isolated system. What was an isolated system? We're going to use conservation of momentum when we have an isolated system. What does that mean? Cody? Well, okay, that's the law of conservation of momentum, but and that's absolutely true. The total momentum stays the same even if the individuals change. But that's true only if we have an isolated system. The isolated system is what? Yeah, it's a system where we don't have any external forces. The reality is there's almost always going to be external forces, right? So we've got to account for that in one of two ways. One, like literally take them into account in the problem. If there's a third object colliding, which provides an external force, we've got to include that with our analysis so that it becomes an internal force. Or the other thing we can do is just look at immediately before and immediately after the collision so that no external forces like friction or so on have a chance to actually do anything, any measurable amount anyways. All right? So if we have an isolated system which no external forces act, we can use this new law that we learned yesterday, the law of conservation of momentum. Now, having said that, even when we analyze something using conservation of momentum, understand that impulse still applies. We just have to treat it differently. Okay, if we're treating it using impulse, we have to make sure that we're looking at one of the objects or the other, but not both of them at the same time. Now, impulse, you guys learned last week, came from one of Newton's laws. You guys remember which law it was? Yep. Yeah, Newton's second law. If you remember, we derived the equation for impulse, F delta T is equal to M times delta V, from the F is equal to M times A equation, which is really just Newton's second law. Yesterday, you learned that the law of conservation of momentum comes from another one of Newton's laws, that law being the third law. The third law says, if object A applies a force on object B, then B applies an equal and opposite force on object A. In other words, for every action, there's an equal and opposite reaction. So when we do impulse, we're really just doing Newton's second law. When we do conservation of momentum, we're really just doing Newton's third law. We're just doing it in a new physics 30 kind of way, which tends to make it a little bit easier. All right. Ultimately, we're going to solve this problem using conservation of momentum. If we've got an isolated system and we understand that we've got to look at every object within that isolated system, it boils down to this. Pi is equal to Pf. The total initial momentum equals the total final momentum. And remember, momentum is m times v. You're going to have an mv term for every object that you have. If there's two objects before the collision, then we'd say m1 v1 initial plus m2 v2 initial. If these two objects stick together and become one object afterwards, then we just have one term, mv. Let's call it mvf actually for final. No subscript for the number of the object, because if they stick together, there is only one. You might as well just call it mv, mvf. All right, we had a number of questions last night for homework on worksheet number 3. I want to give you some answers to that, and then we'll take a look at what we need to do. All right, then let's take a look at questions 3, 4, 5, and 7. Number 3 says, a 5-kilogram ball hits a 75-kilogram man standing at rest on ice. The man catches the ball. How fast does the ball need to be moving in order to send the man off at a speed of 3 meters per second? I don't see anything really to circle in red here. Nothing. I don't think there's anything that's going to lead me to a silly mistake. I might make a mistake, but if I do, it's going to be a mistake that is a I don't know what I'm doing kind of mistake, not a silly mistake. So let's just write down some givens here. We know that M1 is 5.00 kilograms. M2 is 75 kilograms. What else we got here? Say V1 initial. The initial velocity of the 5-kilogram ball is, that's what we're looking for, isn't it? V2 initial, the velocity of the man is 0 meters per second because it says he's standing at rest on ice. What is this? V what? 3 meters per second. Yeah, right? Yeah, we're just going to call it VF, right? We're not going to call it V1F or V2F because it's both of them. They're stuck together. All right, PI equals PF. We're going to say M1 V1I plus M2 V2I. What's a little shortcut right now? What is V2I? Okay, what's M times V2I? So I can just write in 0 here if I want, right? I mean, you could even skip that entirely, right? I usually write it in just to kind of remind myself that the object is there. MVF, one object. M1, 5 kilograms. V1I is what we're looking for. Equals the combined mass of 80 kilograms times VF is 3. 80 times 3 is 240 divided by 5. V1I ends up being 48.0 meters per second. Can you explain to me why after the guy catches the ball, he's moving at 3 meters per second, but the ball is moving at 48? Like, if we have the same momentum from one point in the question to the next, how is the velocity so much lower? Yeah, because the mass is so much higher. It was all of that momentum in a 3-kilogram ball. Now it's all of that momentum in an 80-kilogram system. So, of course, the velocity's got to go down to accommodate for the increase in mass. Good there? All right, number 4 is our next one. Of course, there's a 1,500-kilogram car traveling at 100 to the south collides with a 1,200-kilogram car traveling north at 100 kilometers per hour. Heavier car continues to move south after the collision. Slows to 25. How fast is the lighter car moving? I think we got an issue of south and north here as well, right? Oh, what else do you see there that's kind of red circle-able? Kilometers per hour. I'm going to circle that in green, actually, because start putting too much red, it stops drawing attention to things, right? It's kind of like those people that highlight everything on their page. It kind of doesn't draw attention to things anymore if it's everything that's highlighted, right? Whatever system you want to use, I don't care. Just draw attention to things that can lead you to a silly mistake. You're going to see in a second, actually, that the green one, I could have actually gotten away without doing that because the units actually don't matter here. Just patiently wait for a second. I'll explain why the units don't matter. All right, what do we got here? Mass 1 is 1,500 kilograms. We're going to say V1 initial is negative 100, or we're going to make it negative 27.7778. We're going to say that M2 is 1,200 kilograms, and we're going to say that V2I is positive 27.7778 meters per second. The heavier car, that's the first one, V1 final, is moving at negative 25 kilometers per hour, negative 6.944 meters per second, and we're looking for V2F. Let's say PI equals PF. You could, right? You could analyze this using impulse. You could say the impulse experienced by the heavy car is delta P. You know what the mass of the heavy car is. You know what delta V of the heavy car is. Then you could say that's equal but opposite to the impulse experienced by the light car. So now we know what delta P is for the light car. We know what M is for the light car. We could determine what delta V is for the light car, right? That work? Sure it does. I just don't think it's the most efficient way of dealing with it. I think the best way of dealing with it is PI equals PF. Instead of analyzing one object at a time, analyze the system altogether. Conservation of momentum as opposed to impulse. All right, two objects, M1 V1I plus M2 V2I equals two objects afterwards, M1 V1F plus M2 V2F. Now, I told you a minute ago that it didn't really matter what units you used here. Can anybody explain to me why, now that you see what I have written on the board? Yeah, right? Good. It's not the same number in every term, so you can't cancel the number, but the units are the same in every term. So whether you're talking about kilometers per hour, meters per second, it doesn't really matter, as long as you're consistent through the question. Now, if that confuses you, what should you do? Just go to meters per second, right? You can't go wrong going to meters per second. It's just a little bit more work than you have to do on this question. You know what? That's what I did. I went to meters per second, even though I know I didn't have to convert units. I still did, because it's habit. And I want to stay in that habit of converting units, because in most questions, you need to convert. So what do I got here? 1,500 kilograms times V1I is negative 27.778 plus M2 is 1,200 times positive 27.778. M1, V1F is negative 6.944. M2, solving for V2F here. Let's pull out the calculator and solve this as a group just to make sure that we can all do it here. See, 1,500 times negative 27.7778, negative 441,000. Let's add to that brackets 1,200 times 27.7778. There's my left-hand side. Now, what do I want to do with the 1,500 times 6.9? Yep. Subtract the negative. You want to, it's a positive 1,500 times negative 6.9. So subtract a negative value, or you could just simply add it, right? If you pull the negative up front here, put it here, then it would be the same as subtracting on the right side, adding on the left side. So let's add 1,500 times 6.944. Like, you got to get these signs right. Period 2, there was a couple people consistently messing up on the sign. It's just missing the negatives. And you get the wrong answer every time you do that. Now, if it's physics 20 and we mark a question at a 5, you get a 4 out of 5 probably for that, right? But if it's physics 30, when we mark a question out of most of the questions, at least at a 1, you get a 0 out of 1 for that. You don't want to do that. So there's all those numbers. Let's divide it by 1,200 now. 1.74. As a couple of people I think noticed, that's not a practical answer because it means the two cars are going right through each other, which of course can't happen. But with the way that I have the question set up, which is flawed, of course, mathematically this is what it works out to be. Next one, number 5. 92-kilogram football player running at 6.5 to the north collides with an 85 running to the south. Right away, we see the north and south. 92 football player continues moving at a velocity of 2 meters per second after the collision in the same direction, presumably. What's the velocity of the 85-kilogram football player after the collision? So what do we got here? M1, 92.0 kilograms. Say M2 is 85. What's this? V something is 6.5. Tell me what that is. Is that V1 or V2? Yeah, it's V1I, V1 initial. We got another one here that's -6. Negative because it's to the south. What's that? V1 or V2? V2 what? V2I or V2F? V2I. Next one, V is equal to positive 2.00 meters per second. V1 or V2? V, it's going to be V1, object number 1. V1I or V1F? Initial or final? What is it? Final, yeah. Looking for V2F here. So let's, again, you could use impulse if you analyzed one object and then the other. But let's just do it all at once using conservation of momentum. We got two objects before and two objects after. M1 V1I plus M2 V2I. M1 V1F plus M2 V2F. We said a few minutes ago, units cancel, right? But numbers don't cancel. Is there ever a time when numbers might cancel here? It doesn't happen in this question. But is there ever a situation where a number could cancel out of one of these conservation of momentum problems? Okay, mass 1, 92 kilograms times V1I, 6.5, plus 85 times -6, 92 again times V1F is 2, 85 times V2F. Now, when we do the math on this one, it's the same as it was on the other one. Calculate this, subtract this, 85 times 6, because there's a negative in there. Take this to the other side by subtracting this time, because it's positive, and then divide by 85. When we do, we end up getting V2F, negative 1.13 meters per second to the south, which, just like number 4, the question is flawed. Here we have the football players running straight through one another, which of course can't really happen in real life. Finally, number 7. I love this question, number 7. It says a person holding a 15-kilogram gun containing one 50-gram bullet. Right away, I'm draw attention to that. Even if I decided to go with grams, I got to be consistent through the question. If you're going with grams, stick with grams. Riding on a train that's traveling at 75 kilometers per hour to the east. I know that I could go with kilometers per hour, but I'm going to convert to meters per second just to stay in the habit. Man fires the gun and the bullet moves off 350 meters per second to the east. Relative to the train, it's the velocity of the gun relative to the ground. That's the confusing part there. The fact that we've got two different frames of reference there. How many of you guys have ever been on one of those moving walkways at an airport? You guys know what I'm talking about, right? It's like an escalator, except it's like just flat. It's almost like a treadmill, right? Except kind of going kind of slow. Like you have to walk like a kilometer through the airport to get to your gate. And then they have this moving walkway that goes for about 40 meters. I'm not like, so I don't know why exactly they have them, because in the end it saves you. So you have to walk now 960 meters instead of 1,000 meters. But anyways, you know what I think they have them for? I think they have them, honestly, because sometimes you have to sit in the airport for 2 or 3 hours. You got to have a way of entertaining yourself. So yeah, go for a walk on these moving walkways. Exactly, backwards on them, exactly. Go opposite to the way that it's going. It's exactly what people that like to have fun do. If you've been on one of those moving walkways, you know that if you stand on the moving walkway, that you're moving at 0 meters per second relative to that walkway, right? If you look down and you see that black treadmill belt basically that's pulling you forward, you're not moving relative to it. But if you look at the magazine store that's next to the moving walkway, you can tell you're moving relative to the magazine store, right? So there's two different frames of reference there. Relative to the moving walkway, you're at rest. Relative to the magazine store, you're moving. We can have two different velocities depending upon our frame of reference. You're going to see how this comes into play here in this question in just a moment here. What I want to do for this question is pick a frame of reference. I can't solve this question from start to finish and use both frames of reference as I'm doing it. I've got to pick one. My frame of reference that I picked was the train, relative to the train. You could have just as easily picked relative to the ground and it would be just as correct. I picked relative to the train. Just like you're analyzing the problem of you on the moving walkway at the airport, you could pick the walkway as the reference point. You could pick the magazine store as the reference point. Okay, I'm picking the train as my reference point here. If that's the case, then we're going to say M1 is 15 kilograms. And we're going to say M2 is 0.050 kilograms. We're going to say that the train is traveling at 75, but you, or the gun and the bullet, relative to the train is 0. I mean, think about that. The train is at rest. Well, the bullet and the gun are clearly at rest. The bullet is the train is moving at a constant speed. Well, the bullet and gun are still moving at that same speed and at rest relative to the train. If you're in that train and you have a cup of coffee and you take a sip of it, like you don't spill the coffee, right? Okay, relative to the train, the coffee cup is at rest, even if you're moving at 75 kilometers per hour relative to the ground. All right, so what else we got here? V2, we're going to say V2F. That's the final velocity of the bullet relative to the train is 350. I'm going to solve for V1F, which is not really what I'm looking for. That's going to be the velocity of the gun relative to the train. I want it relative to the ground, but we'll deal with that later. Pi equals Pf. Relative to the train, the initial momentum is, quick, easy answer here. What is it? 0. The whole thing is at rest relative to the train. M1 V1F plus M2 V2F. M1 is 15, V1F, that's what we're going to try to find here. It's not my final answer though. M2, 0.50 times V2F is 350. We would expect the gun to move backwards slower than the bullet, right? Same momentum, but much bigger mass, so it's going to end up going much slower. We end up getting for V1F negative 1.16667 meters per second. Now, let's go back to the moving walkway for a second here. If I'm on a moving walkway that's moving at 5 meters per second to the east, and I walk at 2 meters per second to the east, how fast am I moving relative to the magazine store over there? It's moving at 5, and I'm walking on it at 2. 7, okay? To the guy that's standing waiting to pay for his magazine, he thinks I'm moving at 7 meters per second. Relative to him, that's correct, right? What if though the moving walkway is going to the east at 5, but I'm walking opposite because I'm trying to have some fun to kill some time at the airport. I'm moving opposite at 2 meters per second. How fast do I appear to be moving to the guy buying the magazine now? 3. Right? How do we get both of those numbers? Well, we added. Right? We added them together. We added 5 plus 2 is 7. 5 plus negative 2 is 3. How do we get the velocity of the gun relative to the ground? Well, we're going to add 20.833, which is this number right here, plus negative 1.1667, which gives me 19.7 meters per second relative to the ground. How many people solved it this way using the train as my frame of reference? Okay, how many people solved it the other way using the ground as your frame of reference from the beginning? Okay, 6 to 1, half dozen of the other, right? Ends up giving you the same thing, of course.